We're going to begin with how critical numbers are even defined. What actually is a critical number? If a function defined at f of c exists, so let's number these here. So if f of c exists, has to be a point, has to have a value, can't be a whole, it has to actually exist. So if a function defined at f of c exists, and if f prime of c equals 0, so at the point c, the slope equals 0, or the slope does not exist, meaning that it's just that the slope is, like, for instance, it's like this. Imagine this is our point that we're looking at. If it's straight up, slope does not exist. So if it's 0 or it does not exist, then c is a critical number. So really, all a critical number is a point that, well, it exists, obviously, and it's a point where the slope equals 0 at that point, or it does not exist. So for instance, if I have a graph and I have my parabola right here, and I have this point at the bottom. At this point, the slope equals 0. Let's just say that this point exists. The slope equals 0 here. You would call this a critical number. And the same would be true, like that example I just showed. If it was like this, for instance, and it kind of has this shape to it, and we have our point right here, because the slope does not exist, and the point itself exists, then that would also be a critical number. Now, critical numbers are involved mainly when dealing with solving for extrema. Let's draw another graph to visualize what extrema are. Just think of extrema simply as maximums and minimums. So we have our graph here, and let's just say that our points are as such. I'm just going to make a little line here. This is straight from the notes itself. So let's imagine this is our line. Let's just imagine that this is our line. Now, we have our max, our maximum, and we have our minimum. Now, we also have these points right here. These are also maximums and minimums. However, they are called relative maximums and minimums. And this is where you have to differentiate between absolute maximums and minimums and relative maximums and minimums. To put it simply, an absolute max or minimum is, well, just that. It's the absolute point on a graph where a graph hits its highest and where a graph hits its lowest. A relative maximum and minimum, these can be thought of as turning points. Turning points. So they're just points where the graph changes from increasing to decreasing. It's just where it changes direction. So, for instance, notice how this portion, this portion right here, we start decreasing, and then once it hits that point, it starts increasing. It changes direction. We would call this a relative minimum, because as you can see, it's at the bottom. And now, right here would be the same deal, except it's just the reverse. It increases, and then it starts to decrease. So you would call this a maximum. So relative minimum and relative maximum. Bearing all that in mind, there is an important note to be made here. So relative maximums and relative minimums are turning points. Absolute maxes and minimums don't have to be, as long as, like, for instance, let's say that we have just a straight line and we have points here that show where it starts and where it ends. This would be just the absolute max and the absolute minimum because there's no turning point. It is simply where the graph is at its lowest and at its highest. So those are just what the max and the min are. They're just a maximum and a minimum. Relative maximums and minimums have to be turning points. So with that in mind, let's make a note here. If f has a relative minimum or maximum at x equals c, then c is a critical number of f. So if the function f has a relative maximum or minimum at x equals c, so f of c, then c is a critical number of f. If we know that it's a relative minimum or a maximum, we know that the slope has to be either 0 or DNE at the point C, wherever that is. Wherever C is, right? Let's just say that this could be C or this could be C, right? In this case, it is a maximum, and in this case, it is a minimum. But we see that the slope equals 0 because it has to change direction. So if it's a minimum or a maximum, then we know that the point C is a critical number of f. However, the converse is not true. Just because a critical number exists doesn't mean that there's a relative maximum or minimum at that point. For instance, just on the graph. Let's say, for instance, that we have just a normal cubic function. In our cubic function, which is just simply f of x equals x cubed, we can see that the slope goes to equals 0 at the origin. However, it doesn't change direction. The function itself is always increasing. It doesn't change to go down. So while the origin 0, 0, while it is a critical number, because the slope equals 0 at that point, it does not have a relative maximum or minimum at that point. So to reiterate, if a relative maximum or minimum exists at a point, then that point must be a critical number. However, just because something is a critical number doesn't mean it has to be a relative max or min. With all this in mind, though, you might be wondering, how do we actually find critical numbers? What is actually the mathematical method for finding them? There are a few steps. So let's say you have a function, and let's just say whatever it is. We'll just go over the steps and then we'll go over some examples. So f of x equals something. The first step is finding the derivative. So you want to find f prime of x. That's the first step. The second step is finding where f prime of x equals 0. And if necessary, you also need to find where f prime of x equals dne. Those are the only steps to finding critical numbers. So let's go over a couple of examples. I'm going to take this and shrink it over here. So let's start with a simple example. We have f of x equals x squared times x minus 3. Well, the first thing that we're going to do here is we're going to expand what we have. So we're going to have f of x equals x cubed minus 3x squared. Now that we have expanded this, now we're going to find the derivative, which is 3x squared minus 6x. Now that we have found the derivative, all we need to do is set it equal to 0 in this case specifically, and I'll go over that in a minute. So we're going to set f prime of x equal to 0, so 3x squared minus 6x equals 0. Now we're going to factor this really quickly. We can take a 3x out, so 3x times x minus 2 equals 0. And here we find the values of x equals 0 and x equals 2. So these would be our critical numbers. The reason why in this scenario we only have to find where x equals 0 is because with this equation specifically, there's no number that you can plug in to make it so that f prime of x does not exist. However, there are functions for which you will plug in x values that it will result in an answer that does not exist. These are particularly with functions that have fractions in them. Now, this can come in many forms. Sometimes the function itself is just a fraction, or it might have an exponent in it for which when you find the derivative, you'll get a fraction. An example of having to use step 3 would be for the function f of x equals x to the 1/3 power. Finding the derivative of this, we get 1/3 times x to the negative 2/3, which if we're going to simplify this to make it look better, we would get 1 over 3 times the cube root of x squared. Now, you may notice that this is just a 1 alone. There's no x value. So we don't have to worry about step 2 then, because if the numerator is just 1, then there's no point where f prime of x equals 0. It's just 1. The numerator is just 1. So we don't have to worry about that part. We only have to worry about this bottom portion. So we're looking for when f prime of x equals d and e. So really, what we're solving for is, since we're just trying to look for when the denominator itself is equal to 0, all we have to do is write 3 times the cube root of x squared equals 0 and solve for x. When we do that, and we go through the steps here, we get the cube root of x squared equals 0. Then we get x squared equals 0. And then we get x equals 0. Let me rewrite that. X equals 0. So this would be our critical number. That's an example of having to solve for d and e. This was a brief introduction on critical numbers. They'll be used a lot more frequently over time. But for the time being, hope you have a somewhat clearer understanding. And we'll go over these in future videos as well. So you'll probably get to see them there to get a more clear understanding if you don't have one already. I do hope this video helped you though, and there will be more videos to come. Thank you for watching, and peace.